The next topic I want to talk about is integrals that involve certain factors. We're going to have a positive number a, and u can contain our variable, usually x, but not always. We're going to look at some integrals that involve a factor of square root of a squared minus x squared, also a squared plus u squared minus a squared. In the first two, things are going to be perfectly straightforward. If I have a factor that looks like this, I'm going to make a substitution. I'm going to let the u equal a times sine of theta, where theta is in the range from negative pi over 2 to positive pi over 2. The reason that we pick that range of theta values is those are the numbers that the inverse sine can produce. So at the end, when I want to undo everything and express the answer back in terms of x again, I'll be able to use the inverse sine to do that. If I have a factor that's square root of a squared plus u squared, we will use u equal a times tangent of theta. The range of theta values that we'll use is practically the same as for the sine, except of course tangent isn't defined at pi over 2 or negative pi over 2, so we have to leave those out. If we have a factor that looks like radical u squared minus a squared, we'll let u equal to a times secant of theta, but then life becomes much more complicated than it was in the first two types. As an example, let's look at the integral of 10 over x squared radical 25 minus x squared with respect to x. Looking at the pattern, a should be 5, so that this number is a squared. My u will just be x, and I'm going to make that equal to 5 times sine of theta, where theta is in this nice range of theta values. If you figure out what 25 minus x squared is, it ends up being 25 times cosine squared of theta. So the radical that we're talking about is literally 5 times. There's a possibility for a little bit of confusion here. If you wanted to be picky about it, you should say absolute value of cosine theta. But in this next line, you see that I didn't, because if you're in this range of theta values, the cosine's positive when theta is negative 90 degrees to positive 90. That's why I can just stop writing these absolute value symbols down. If x is 5 times sine of theta, the derivative of x with respect to theta is 5 times cosine theta, and the dx is 5 cosine theta d theta, which is where this bit came from. The rest of it, I'm just writing down the individual pieces of my integral. Factor a constant out. The reciprocal of sine squared is cosecant squared, and that's one of the things we know how to integrate. It's on our list. Its integral is negative cotangent of theta. Now, when it comes time to write it back in terms of x's again at the end, what people usually do is they draw a little triangle like this. X was 5 times sine of theta. That means sine of theta has got to be x divided by 5. Make up the easiest triangle so that the opposite over hypotenuse will come up what you need it to be. I put theta here. I'll call this number x and that number 5. From the Pythagorean theorem, you can figure out the other side. By doing it like this, sine of theta is x divided by 5, like it's supposed to be. So I want to write down the cotangent of theta. If I was writing the tangent of theta, it would be opposite over adjacent. The cotangent is the reciprocal of that. So I end up with the square root of 25 minus x squared over x, and then add the constant of integration in. A slightly more complicated problem. I want to find an antiderivative for radical 64 minus 49x squared. 64 is 8 times 8, so the a number is going to be 8. The thing that I'm subtracting away is the square of something. It's the square of 7 times x. 7x is what we're thinking of as being the u here. 7x is going to be a times sine of theta, where theta is in the nice range. If you put that into the square root factor, you find out that the square root just turns into 8 times cosine theta. You can actually solve for x in terms of the other stuff by taking this formula and dividing through by 7. The derivative would be 8/7 cosine theta. So dx is just going to be 8/7 times cosine theta d theta. And we have all the little bits we need to set our integral up now. Writing in all the little bits, combining some factors, pulling constants out front, it turns into 64 divided by 7 times the antiderivative of cosine squared of theta, d theta. Now, we have a trig identity that lets us write cosine squared in terms of just cosine to the first power. So use that identity. 32 over 7, antiderivative of 1 with respect to theta is theta, and an antiderivative for cosine 2 theta is 1/2 times sine of 2 theta. Now, there's a trig identity that says sine of 2 theta is 2 times sine theta cosine theta. So I'm going to use that to reduce the sine of 2 theta down. And here's the problem that we have to deal with in order to finish the problem. It's written in terms of theta, and I don't want that. I want my x's back again. So I'm going to have to figure out what theta is in terms of x, figure out what sine and cosine of theta are, multiply those two together, and add it in. We want sine of theta to be 7x over 8. So again, be as lazy as you can be. Put 7x over here and 8 there. Use the Pythagorean theorem to find the third side. And now I can calculate any trig functions of theta that I feel like. In my antiderivative, I actually had theta all by itself. Because of the range of theta values that we're using, it's safe to say theta is inverse sine of 7x over 8. Cosine of theta, now that we've got our triangle, cosine theta is adjacent side divided by the hypotenuse. Sine of theta was 7x over 8. So here's where we use the inverse trig function. That's sine of theta, that's cosine of theta, and this is my answer. If you have integrals that involve factors that look like a squared plus u squared, the substitution that we're going to use is u equal a tangent theta, where theta now is strictly between negative pi over 2 and pi over 2, because the tangent isn't defined at those places. A squared plus u squared, after you factor it up and use a trig identity, turns out to be a squared times secant squared of theta. And if I needed to do the square root, it would still be okay, because in the range of angles we're looking at, the secant, which is the reciprocal of the cosine, is positive. Let's find an antiderivative for x cubed over 4 plus x squared. In view of what we said a minute ago, the a is obviously going to be 2. The u is going to be 2 tangent theta. So I'm going to let x be 2 times tangent of theta, where theta is in this range. The 4 plus x squared, using this same trig identity again, turns out to just be 4 times secant squared of theta. Then put in 2 tangent of theta wherever you see x other than this denominator. You have an x cubed, so you have 2 cubed tangent cubed of theta. You also have to write dx in terms of theta. The derivative of 2 tangent theta is 2 secant squared theta. Dx is 2 secant squared theta d theta. So all of the bits in the integral, including the differential bit down at the end, have been converted over into references to theta rather than x. Obviously, there's going to be some canceling out here. The secants canceled completely out. I combined all of the constant factors into a single 4 and pulled it out in front of the integral. If you remember what you were supposed to do when the power on the tangent is odd and positive, you're supposed to pull a tangent secant out. So I'm going to take one of my 3 factors of tangent and write it down by the differential. There is no secant in this problem, so when I put a secant factor here, I have to put it in the denominator so that it cancels out and gives me what I had before. The reason that we're going to do this is, having removed one of the odd powers of the tangent, only even powers of tangent remains, and we can use our trig facts to convert that into secants. So everything in the integral except that we can write in terms of secants. But see, this is what we want, because the derivative of secant is tangent theta times secant theta. So I'll make a u substitution, let u equal secant of theta. Du is tangent theta secant theta d theta, which is that. In terms of u, you're going to integrate u minus 1 over u with respect to u, and then you're going to multiply that by 4. That's easy, of course. Antiderivative of u with respect to u is 1/2 u squared, and antiderivative of the reciprocal function is natural log absolute value. So we've got it down to here. This u is secant of theta. So putting the secant of theta back in, this is my antiderivative. And then we have the same issue that we had before. This is written in terms of theta, and I want it written in terms of x for my final answer. So x is 2 times tangent of theta. X over 2 is tangent of theta. Put an x opposite theta, put a 2 adjacent to it. The Pythagorean theorem tells me this length is radical 4 plus x squared. And then I can calculate any trig functions that I feel like calculating. When I put everything in and simplify it, I end up with this quantity as my antiderivative. The remaining case, where you have quantities involved, u squared minus a squared, we're going to make a substitution, all right. We're going to do u equal a secant of theta, but we run into a problem that we haven't run into before. We need to talk a little bit about the secant function. The secant function is the reciprocal of the cosine function. On the interval from 0 to pi radians, the cosine looks like this. This is the chunk we used when we built the inverse cosine function. If you look at the piece of the cosine that we used to build arc cosine, it goes from x equals 0 to x equal pi. All values of the cosine function from 1 to -1 get taken on, and at pi over 2, the cosine cuts across the x-axis, which is going to have an unfortunate consequence when we look at the secant. The secant is the reciprocal of the cosine function. So when the cosine is equal to 1, the secant is also equal to 1. The cosine remains positive for a while, but gets close to 0 as you approach x equal pi over 2. So you're going to be taking the reciprocal of a positive but small number, which will give you a big positive number. So for the theta values between 0 and pi over 2, the secant is always at least 1, and as you approach x equal pi over 2, it becomes very badly behaved. You have a vertical asymptote. At the other end, when x is pi, cosine of that's -1. The reciprocal of that is -1 again. If your angle is just a little bit bigger than pi over 2, the cosine will be close to 0, but it'll be negative. So you'll be taking the reciprocal of a negative number of small absolute value. That will give you a negative number with really big absolute values. So if the angle is between 0 and pi over 2, secant's at least 1. If you're between pi over 2 and pi, the secant is never bigger than -1. If I'm going to make a substitution where u equals a times secant of theta, this is going to correspond to the u being bigger than a, and this will correspond to the u being smaller than -a. There's something else bad going on here as well. The tangent, which is going to figure into this in a moment, is positive if theta is between 0 and pi over 2, but it's negative if theta is between pi over 2 and pi. So we're going to make a substitution. X is going to be a secant of theta, and depending on whether x is positive or negative, I'm going to get different behaviors back from this square root symbol, which we'll have to calculate. And recall, principal square root of something is never negative. If we actually think of doing this kind of substitution, we would have, under the radical sign, a squared secant squared of theta minus a squared. In the two terms underneath the radical, I can factor an a squared out and actually go on and split it completely out of the square root. We always think of a as being positive, so square root of a squared will just be a. But this is kind of a problem. The square root of the square of something is the absolute value of the thing. And the problem is, I'm going to have to discriminate between two different cases depending on whether the tangent is positive or where it's negative. So what's going to happen is square root of a squared secant squared theta minus a squared is a times tangent of theta if the angle is between 0 and pi over 2, which corresponds to x being larger than a. Otherwise, if you're over in this range of theta values, then the tangent is going to be negative. A times tangent will be negative, and I have to stick a minus sign on it to get the correct value back. As an example of all this, I want to find an antiderivative for 1 over x squared times radical x squared minus 1 with respect to x. And to avoid any of this plus or minus sign confusion, I'm going to assume that x is bigger than 1. That means that this radical sign will just simplify down into tangent of theta. X is 1 times secant theta, dx is secant theta tangent theta d theta. The square root simplifies to tangent of theta since I'm presuming that x is bigger than 1. Take all the little pieces and put them down in the integral, and you get the integral of 1 over secant squared theta times tangent theta multiplied by secant of theta tangent of theta d theta, and a miracle happens. Almost everything cancels out, and the reciprocal of the secant is the cosine. Antiderivative of that is sine of theta plus a constant. On one level, we're done. We have our antiderivative, but it's not entirely satisfactory because it's written in terms of theta and not the original variable's x. So we'll have to fix that. Some people would rearrange things as follows. They would say that since x is equal to secant of theta, theta must be the inverse secant of x, and write your answer as sine of inverse secant of x plus a constant. That's not how most people do this kind of thing. Draw a triangle, a right triangle, and call one of its angles theta. What we know is that the secant of theta is supposed to be x. If I were doing cosine, I would have adjacent divided by hypotenuse. If I want the, excuse me, if I want the cosine, I would have 1 over x. If I want the secant, I would have x over 1, and that's our substitution that we used. Then I can use the Pythagorean theorem to figure this distance out, and I can calculate any trig function of theta that I care to now. Our antiderivative worked out to be sine of theta plus a constant of integration. Sine of theta is opposite divided by hypotenuse. So I'll just write that down. Most people would do it this way, feeling that it looks better than saying the inverse secant and the sine thing. Coming soon, the method of partial fractions. I hope everyone has a good weekend and a safe 4th of July.